Chen over here, and today I'll be talking about wave optics, an overview of the general ideas in wave optics, more in the context of A levels. So, by the way, because I'm not foolproof, please read the description for any errors, because I will not retake the entire video. I will post the description. I'll post the errors in the description, and please leave a comment or tell me if there's any errors. So, first of all, overall, difference between wave optics and geometric optics. Geometric optics, you might deal with lenses and stuff. Well, when do you differentiate the two? When you have the wavelength of light, as you know, light is an electromagnetic wave. There's a wavelength. When the wavelength is much smaller than the object it interacts with, then um, it can be approximated that light travels in a straight line and is represented by basically a beam, a straight line, and hence resulting in the field of geometric optics where you have lenses and then you think of light as a straight as traveling in a straight line. Yeah, but when you have when the wavelength of light is comparable to the size of the objects it interacts with, for example, a really small slit or really small like a strand of hair or something, then when it becomes comparable, then the wave nature of light starts to take over, and instead of having light as going as a straight line, you need to think of light as more of a wave, and hence resulting in the study of wave optics. Lastly, as a side note, there is also quantum optics when the because light is both a particle and a wave, but the condition sometimes it's better to think of it as a wave, sometimes it's better to think of it as a particle. When the quantum of nature of light starts to emerge, for example, when you're considering hitting using photons to hit molecules, where you can excite an electron from the ground state to a higher energy state. When the quantum nature of light starts to become important, then there's under the study of quantum optics. So what we're studying in this case is the regime of wave optics in this video. So overview, wave optics is guided by the principle of Huygens principle, which is basically saying that at a wave front, um, each point on the wavefront acts like its own source. So basically, you can think of light as it travels. Every single point of the light it starts creating a new spherical wave at that point. Well, it doesn't seem intuitive at all, and in fact, this principle is still debated now that even after many years, it's still debated. So if you would like to read about the nuances and the limitations of Huygens principle, then you can go ahead to go to the wiki. But um, for in A-level physics, you can just take Huygens principle as a given, because we're going to use Huygens principle to derive to explain quite a lot of phenomena such as diffraction or interference. So yeah, just take Huygens principle as a given, even though it is good to be aware that it is still debated and it's not the most perfect law. So there's one major confusion that I used to have about wave optics, which is the difference between a single slit, a small slit, and a big slit. So the distinction is that if you have a single slit and light goes through, then the single slit acts like a point source. What do I mean by single small slit? I mean that when the size of the slit is really small, at a limit that it tends to zero, that's a small slit. So if the slit is really small, then you think of it as a single point source. But if the slit is big, in that it has a finite size, then it is important to think of the the big slit as a continuum of sources. So you can see that these two cases will make a huge difference in the behavior of how the light uh, after it passes through. So this is a small summary first. I'll go through a simple example of double small slit and then single big slit. Then we'll see what happens when we combine the two cases and get a double big slit, and then after that I'll go on to discuss many slits. So first for double small slit, if you have double small slit, remember that it's small, so each slit acts like a point source. Okay, each slit acts like a point source, and so let's say that So we want to determine the interference pattern on the screen, right? So we think of each slit as a point source, and it starts it's two coherent sources, so they emit light at the same time. You can think of the wave going out in sync. However, because if you have a if two parallel rays travel like this, and because there's a difference in length that they travel, which is indicated by the red part here. Because there's a difference in length, there will be a small phase advantage that this one has. So this one will have a phase difference with this light. So the wave that coming from here and the wave coming from here there's a phase difference caused by the fact that when you shine off at an angle, there's the rate difference, the rate path difference. So if you do maths on it, you'll see that this is a triangle and the rate distance is d sine theta. So if it's a multiple of the wavelength, then there's constructive, and if it's half integer multiple of a wavelength, then it's destructive. So so what this means is that, let's say we're given a slit of a double small slit over here, and then we have a screen. Okay, so let's ask the question. I choose a point on the screen and I want to ask, is there light or not? So what I do is I draw the straight line from the screen to roughly where the two slits are, and I measure the angle, and then this angle theta will be the one I plug into the formula. Wavelength usually is given, and I just need to check if it's an integer multiple. So that's how you apply this formula over here. But what if it suits neither cases? Because sometimes it might not, the d sine theta could take on a value that's not a half an integer multiple or integer multiple from the wavelength. So if the answer is that the intensity you see on the screen is a spectrum, so what the formulas we have, d sine theta equals n lambda and n plus 2 and n plus half lambda. Now these formulas are for the extreme points on the intensity graph. So if this is an intensity graph, it'll be like something like this nature. Then what you'll see is the green points, which is the constructive interference, will be given by this. And yeah, so to answer the question, what if it's neither cases? If it's like somewhere in between, like maybe where my mouse is right now, then it will neither be completely destructive nor completely constructive, but it'll be in between. Yeah, the intensity will not be as bright as the constructive place, but neither would it be as dark as the destructive place. So yeah. So now so we have gone through what happens for a double small slit. Now for a single big slit, so you have a big slit over here and light goes through, and then at an angle theta that all the light rays go parallel from, each point that is a continuum of point sources. Over here I drew a few dots. I drew 6 dots, right? But you must imagine that there's actually uncountably infinite number of single point sources. So it's a continuum. It's like it's like the real numbers. It's continuum of point sources. So so it turns out you can come up with a condition for destructive interference, but there's no condition for constructive interference. So the destructive interference condition is this. Okay, this is for destructive interference. But do note that this is you see this formula in the double small slit, right? But this formula for the double small slit is for constructive. So it is important to note that this formula, when applied to different cases, might mean different things. Yeah. So if you do to do it to calculate it more precisely, besides this only tells us where the destructive places are, but if you want to find the spectrum, the intensity pattern, then we need to do some integral, and I will not go through the details over here. You can find it in the book of competitive physics for physics Olympiad, but you go through some integral and you see that this is the resultant intensity pattern on the screen. So you see sine alpha over alpha, this might be seen as the sine C function, sinc function, and where alpha is defined to be this. So this wave this diffraction pattern on the screen, the intensity pattern, is given by this formula, and we can do note that if d sine theta is a multiple of lambda, then we recover the previous condition for destructive interference. So all in all, when you have a continuum of sources, you need to do an integral, and when you do the integral, you get this result. So what happens when you change the slit size? When the result is that the smaller the size of this single slit, the more spread out the diffraction pattern will be. So in this case, if you have a rather big slit over here, then it's quite pointy. But if you have a very, very small slit, then it'll get more and more spread out. So now for combining the double small slit and the single big slit, what do we get? So when you have a double big slit, then you have a continuum of point sources here, and then you have nothing, and then a continuum of sources again. So this contrasts with the previous double small slit, because in the double small slit case, you have a single point source and a single point source. But for the double big slit case, you have a continuum of point sources and a continuum of point sources. So the upshot is that if you go ahead and do the mathematics, the integral and then the sum, then you get the pattern is a multiplication between a single big slit and a double small slit. So it's well illustrated in this picture here, which I took from hyperphysics. So what happens is you have your multiplication of the single big slit, which is this envelope over here. You can see single slit envelope, this envelope over here, and then it multiplies with the double small slit, which is the small fringes, this small pattern over here. Okay. Now for many slits, so when you have many small slits, you will do a sum, and the sum is essentially a geometric progression. You can use the GP formula. So for double slit, you get something like that. For triple slit, you get something like that, where there's one small maxima in the middle. For 4 slits, you get 2 small maxima. For 5 slits, you get 3 small maxima between the bigger maxima. So yeah, that's the pattern for multiple small slits. And remember, in small slits, each slit acts as a point source. Okay. Now for multiple big slits, you have the single slit, the single big slit envelope, along with the corresponding small slit patterns. So when you have a triple slit and each slit is big, okay, then what you have is the envelope of the single big slit, and that envelope is over the triple small slit interference. So yeah, so there's two, in a sense, there's two patterns over here. One is the envelope, and one is the triple small slit interference pattern. So the phenomena that you call the one above, the small slits here, all the patterns here is known as interference pattern, because they're interfering. The different slits, the different point slits are interfering with each other. So for small slits, you say there's interference. Then for big slits, for the single big slit, you call it diffraction. So the single big slit is called diffraction. And then when you have a double big slit, is both interference and diffraction. So there's a difference between what you call interference and what you call diffraction. Of course, one could kind of argue that diffraction essentially is a lot of interference, but that's what we call it. We call it diffraction. So going from where my mouse is interference, 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 diffraction, diffraction plus interference, diffraction plus interference. Okay, and this is all taken from this website, so you can go ahead and click there and read the explanation as well. Now for diffraction grating, how do we treat diffraction grating? It's essentially uh, infinitely many small slits. So infinitely many point sources, single point sources, but infinitely many of them. And this is discrete. So it's not a continuum. It's not a big slit. It's discretely infinitely many small slits. So it follow the pattern of 2 small slits, 3 small slits, 4 small slits, 5 small slits. And you get a kind of sort of a spiky pattern over here. So that's for diffraction grating. Now for an object, if let's say I have an object instead of I have a piece of hair that I shine light on instead of having a small slit. Well, by Babinet's theorem, you can look it up. It basically says that uh, the intensity pattern uh, for this thing where the highlighted region is blank space. I highlighted it to emphasize as a gap. So the interference pattern for this region for this object is equals to what if you invert the field areas. So it's equals to um, this blank space, uh, something blocking it, blank space, something blocking it, blank space. So essentially are inverting the field area. So by that um, you can treat you can understand the diffraction pattern or interference pattern of an object. So now overall, when you apply formulas, it's important to check whether it's destructive or constructive and not just blindly apply them. Sometimes the question will ask you for destructive, sometimes it asks you for constructive. And in the case of single slit versus double small slits, we saw that one formula for destructive was actually the other formula for the constructive. So it's important to review um, the difference between the two. You can check the lecture notes, they should provide it pretty well. They should explain it pretty well. Now, another important question to consider is when you're given a question, you must think, is the slits big or small? Are these questions asking for big slits or small slits? If they're asking for uh, double slits, then you need to ask, are each of the double slits, the double slit has 2 slits, right? Is each of the slit big or small? Because the result you get on that can be different. So yeah, so that's something important to ask. Now, lastly, I'll end off with a trick that you can use to think about this. I won't go into too much detail, but basically, you can think of waves as, because the wave has a frequency and a phase, right? So, assuming all of them are the same like frequency and there's also amplitude. So, to encode the information of amplitude and phase, there are 2 things, amplitude and phase. To encode amplitude and phase into a single arrow, you can think of it as a phasor. Usually phasor appears in LRC circuits, but I believe that this is applicable to almost any wave with amplitude and phase. So frequency in this case needs to all be the same. So if, for example, you have 4 small slits, right? So because they're small slits, you have 4 point sources. And because you have 4 point sources, you have 4 different waves emanating from it. So 4 different waves, they have rather the same amplitude, so all the arrows are the same length, but they have different phases because they travel different distances. So when they travel different distances, there'll be there'll be a phase difference, phase lag or phase head uh, between them. So what you can do is you can draw it like this, and then what you're saying is the resultant wave that you get from adding all the 4 waves up, all the 4 waves with different phases but same amplitude up, is the vector OP. So this is like any phasor diagram, and then the magnitude of OP is the intensity. So you can easily recover the different conditions required, and this is a useful trick. If you want me to explain it more, please tell me in the comments below or in real life. But yeah, so that's a trick with the phases that you can do. So with that, that's all I have to say. Once again, this video did not cover the derivation of each formula in much detail, but so please refer to your lecture notes for them. But I hope that the main idea was I wanted to convey the difference between big slits and small slits, because it was something I overlooked when I studied wave optics at first. But yeah, with the distinction, things are much clearer for me now, so I hope that it's much clearer for you as well. So yep, have a nice day. Bye.